you're still here, can you please make a mark? It doesn't have to be a signature, just anything in the last column to make clear that goes to here. Right, before we do the flows, which most people don't like, is look at this simplex tableau on the right. Okay, that. That was the final tableau for the chess set problem. Okay, which you may or may not remember. It doesn't really matter. What is? Can you see anything suspicious? Well, if you want to see something suspicious, you should compare the numbers you can see on this side with the numbers you can see on that side. Anything suspicious? So again, the slack variables are the same as It's not the slack variables really, right? But it's these values that you mean. So down here. Yeah, so that is another exciting thing about it, is that when you use the simplex method to solve it, it solves both the final and the dual. And the optimal, when you get the optimal tableau, you will get the solution, the y's everywhere, in the slack variable columns at the bottom. Sorry, in the Z row. Of course, you know, S1 is 20, X1 is 16, and X2 is 46 in the optimal solution. And S2 and S3 are 0. The Z row tells you that the objective, again, is going to be 1160. It's also telling you that in the slack columns, you see Y1 is 0, Y2 is 5/3, Y3 is 83. But also the X1 and X2 columns give you that the two slack variables, surplus variables in the constraints of the dual. Those constraints are going to be specified with quality. So yeah, so that's quite good as well. So if you want to solve one of them, you don't have. Sorry, if you want to solve both of them, you have to solve one of them, and the other one, the other optimal solution, you get for free. Okay. Why? If you want to know why it works, take operational research. It's not very hard to prove. Okay, now let's go to this again. Okay, I believe there are people here who weren't here last week, and so maybe I should say a couple of words again about this. Okay, do you remember the maximum flow problem? I'm sure you do. The maximum flow problem was, or in this variant where it's in one source called S, one sink or target called T, and there are capacities on the arcs of a directed graph. So for example, the arc SB has capacity 5. That's the first number. And a flow, which many people didn't quite get right in their assignment, the flow is not just a number, but the flow is one number sitting on every arc. Okay, so in this case, with the second green number, after the comma is saying is that the flow is 0 everywhere. It's kind of a boring flow, but it's a possible flow. And the flow has to satisfy 3 conditions, I think. Okay. The first condition is that each of these numbers on each arc has to be greater than or equal to 0. You can't have negative flow anywhere. Okay, in our thing. The second condition is that the flow cannot be larger than the capacity on any arc. And the third condition is that when you look at any node other than the source and the target, for example, C, then the amount of flow from A to C, or more generally, added over all arcs that are coming into that node, has to be the same as all the flow added on all the arcs that are going out of that node. Okay? So, stupidly, I forgot the paper from last week where we had some examples of flows. Well, okay, let's now what we can have a look at is, all right, and then, okay, so what we can have a look at first is this formulation. So what you want is this flow, so a number for each arc, okay, and that's what we're trying to find. And it has to be a maximum flow, and I'll say what maximum flow is in a bit. But we have these 3 conditions, okay? So the first condition, flow can't be negative. Okay, that was the first one. Second one is that it cannot be larger than the capacity of that arc. And the third set of conditions is that for every node other than the source and the sink, okay, this is maybe a complicated notation, but when you look at all the arcs which go to U, from anything to U. So the first vertex is some x, doesn't matter what it is. The second one has to be this U that we're looking at. And add all the flows together on the incoming arc. You get some number. And when you look at all arcs that leave U to anywhere, and add all those flows together, you get another number. And this constraint is telling you that the 2 numbers that you get have to be the same. So this is the third condition, as I said, that when you add what's coming into a node, it has to be equal to when you add what's going out of the node. Just a shortened formulation using something. Okay, and so these 3 conditions define a flow. Now, what is the value of the flow? The value of the flow is when you look at the source and add everything that's leaving the source. Okay, in theory, if there were some arcs going into the source, you'd have to subtract what's coming into the source. But let's assume that there are no arcs coming into the source. So what you get as the flow that is leaving the source, that is the value of the flow. And because of these conditions, it must be exactly the same number as what is entering the target. Okay? Because they can't, in any other node, everything is preserved, so whatever leaves the source has to arrive in the target anywhere. Okay? Right. You still with me? So now, what would the dual to this look like? It's a tough question, kind of. Let's have a look at what the matrix this looks like. Okay. The Firstly, actually, when we're doing the linear program in the standard formulation, we need to, what we need is all the decision variables on the left-hand side of the constraint and a constant on the right-hand side. Okay? The third set of constraints, they're not in this form, but we can easily rewrite them by moving everything from the right-hand side to the left-hand side. And so this constraint for every u other than S and T, every node other than S and T, what we get is when we sum of all the FAs over all arcs that are coming into U and subtract sum over all arcs which are leaving U, and we get is 0. Okay? That's just rewriting the third constraint so that we would have all the decision variables on the left and all the constants on the right, and there's only 0. Now, that's that. So if we wanted to write it as matrix, which we don't have to, but I think it simplifies the whole thing. You know, you might not think so at first. So this is going to be the matrix of things. Now, what we're multiplying it with is all the F's, F's. A1 to FAs. And that should be something. So, but this is what we call A in the matrix notation of the linear programming, but it's somewhat unfortunate that I've used A for the set of the arcs. So maybe I shouldn't call it A. But this is the, maybe I should have called the set of the arcs something else. It's confusing. Right. I'll choose not to call the matrix A. Call it M. So instead of AX less than or equal to B, we have M times something less than or equal to B. This matrix M has one row for each constraint. And we have two kinds of constraints. We have some constraints of the type 2, and there's one for each arc. Okay, so we have these rows that are in the, where there's one row for each arc. Okay, and the rest of them, there's one row for each vertex other than the source and the sink. So the matrix has two parts: the top, one row for each arc; bottom, one row for each vertex or node. At the top, there's the identity matrix. Okay. Because we're looking at the constraint 2, and there is everywhere else, so we really get just a big identity matrix. And the right-hand side, well, this is kind of less than or equal and equal here. But what are the right-hand sides? Well, here there's the capacity of these arcs. So C of A1, C of A2. These are the right-hand sides. Okay, and this captures the constraints of number 2. And what captures the other constraint is, okay, this is a bit more complicated. So when you look at the row that corresponds to the vertex U, and the row that corresponds to vertex V. If is if there is an arc A which goes from U to V, then okay, what are the columns? Doesn't look intimidating, does it? The only thing that's intimidating about it is that I'm doing it in generality and not just a silly example. Okay, there is one column for each decision variable, right? Because that's what we have in every linear program. So, and we have one decision variable for each of the arcs. So there has to be one column for each arc. Also, like that, we get the identity matrix, which has as many rows as it has columns because it's the identity. So in that particular column, corresponding to this R, we'll have a -1 where it starts, and we'll have a +1 where it goes to, and we'll have zeros everywhere else. And we'll also have zeros everywhere else in this way. Oh no, we won't. Sorry. We won't have these zeros. But we'll have these. Okay, so +1 where it goes, -1 where it starts. That's because where it starts becomes -1 from the sum over here, and where it goes to, that gives you a +1 in the constraint or the vertex where it starts. Okay, it starts in U. Oh no, where it goes to. So if it starts in U, it contributes -1. Oh, here, and where it goes to, it gives you a +1 into the sum. And there are special things. If you have an R that starts in S, okay, something if starts in S, oh, it doesn't show. Then it only has a +1 somewhere for the node where it goes to. And if an arc ends in T, then it only has a -1 somewhere and 0 everywhere. And that is because we have no row for S and we have no row for T. But S and T don't have a constraint. This is tough. It's especially tough at 5 o'clock in the evening. Is it making any sense whatsoever? Be quite honest. No one's going to. That's what it is. So, I need a big blackboard on which everything would be at the same time. So it's not really like it, and the things, unfortunately, will probably disappear. Okay. We want to do the joules. The constraints will okay, so the matrix of the constraints will be transposed. Okay? So now we will have one constraint for every arc because what our columns are going to become rows. So what our decision variables are going to become constraints. So there will be one constraint for each decision variable, for each arc. And then decision variables will be what was rows. So there will be one decision variable for every arc and one decision variable for every node other than SCT. Okay? So if we want to dualize, I'll cover this for the dual. Decision variable. I will call them X for each arc. YU for each node. Okay. That is because those were our rows. Now they become columns. Really? There's one person please agree. Okay, you don't agree. No, no. Well, not for S&T. Because we didn't have a constraint for the source, we didn't have a constraint for the target, we don't have a decision value for the source, and we don't have a decision value for the target. What is the objective going to be? Okay, the objective on the first one was to maximize something. So in the dual, we go from maximize to minimize. And we go from minimize to maximize. And also for here, we're going from maximize to minimize. So it's going to be now, in the objective, the coefficients of the decision variables will be what were the right-hand sides in the primary. Right? That's the way it works. So these are going to be the coefficients of the decision variables for the arcs, and for the vertices or for the nodes, the right-hand sides will all 0, so all the coefficients are going to be 0 as well. Okay? And that means that what we're going to do is we just have a sum over all of the arcs of the graph, and it will be the capacity of that arc times the decision variable of that arc. Okay. Now the constraints. That's the hard bit. So, how many constraints are there going to be? Excluding any kind of non-negativity. How many constraints are coming in the matrix? Are there going to be any constraints at all? Freddy, please tell me how many constraints there are going to be. 3. Why 3? Oh, but we didn't. There were 3 types of constraints. There weren't just 3 constraints. But what they translated into was, so okay, number 1 is non-negativity constraints, and there were as many as there are arcs. Number 2 was some kind of capacity constraints, and there were not just 1, but as many as there are arcs. And they are here in this bit of the matrix. Okay, so each of these rows in the top of the matrix is a constraint in the original. Oh, let's put the sign there. Should be less than that. It's good that I asked myself a question so this is a slightly dodgy formulation because the top matrix has to be less than or equal to, whereas the bottom matrix has to be equal to the right side. There's not really matrix notation because you couldn't better. But then you forget. Okay, so so each of these rows at the top are saying the first one that FA1 is less than the capacity or equal to the capacity of CA1. Second one is FA2 is less than or equal to the capacity of A2. The last one is FAM is less than or equal to the capacity of AM. Okay, so there are M constraints if you have M arcs in your graph. Okay? Good. And then there are another many constraints, one for every node, except we don't have one for X and we don't have one for T. For any other node, we have one of these constraints. Their right-hand side is 0 because they all look like that. So the right-hand side is 0, the left-hand side is, there are +1s for the arcs that are incoming into that node, and there are -1s for all the arcs that are outgoing. So every row here will have some +1s, some 0s, and some -1s. And the right-hand side will be 0. Okay? And the +1s and the -1s, they're more easily viewed when you look at every column separately, because in every column there will be exactly 1 +1 and exactly 1 -1. Well, with the exception of the columns that start in S or end in T, where there will only be a +1 and only be a -1 in those cases, but otherwise exactly 1 +1 and exactly 1 -1, because every arc goes from exactly 1 vertex to exactly another vertex. Okay? So now I've killed your answer, so we have to go to we don't want to give okay, now, remember we're doing the dual. So when you're doing the dual, I know it's a lot of information at once and so on. But when you're doing the dual, what were constraints become decision variables, and what were decision variables become constraints. Okay? And we had one decision variable in the first formulation for each R. So now we will have one constraint for each R. Okay? So these columns of the matrix, each of them will give you a constraint. And the constraint will be, so there is one for each R, and so there are plenty of zeros when you look at some R. Okay? It's mostly zeros. There's 1, 1 here on the diagonal. There's plenty of zeros. Plenty of zeros, 1 minus 1 and 1 plus 1. And so if A is an arc which goes from U to V, then you get a constraint which says, well, 1 here, which will be multiplied by XA, minus 1 here, which will be multiplied by YU, and plus 1 there, which will be multiplied by YB, and that should be greater than or equal to, so what was the objective now becomes the right-hand side. And in the objective, every arc had a coefficient of 1 because the objective was just the sum of all the fx. So this will be greater than or equal to 1. So this is a typical constraint for a typical arc. Now there are the ones that start in S and the ones that end in T. So if it starts in S, and you could get, then you could derive from here that XA plus YB YB is greater than or equal to 1. If A is an arc that ends in T, then the YV will disappear. So we'll have XA minus YU, who is greater than or equal to 1. And if actually there is an arc directly from the source to the target, and the only thing there will be is that XA is greater than or equal to 1. That is the following. Have you solved it yet? Okay, so I've got a question. In the same chapter as you did maximum flow, what else did you do? With Philip? Well, different question, same answer. On the maximum flow assignment, what was part 2? What did it tell you to give? Minimum cut. Uh-huh. Would there be a link? Was there a theorem, for example? Was there a theorem that the value of the maximum flow and the capacity of the minimum cut are the same? Yes, there was. Okay, so I'll just won't do all the details because I've been doing way too many details already. But let's just have a look at okay. What is a cut in a diagram? Cut is you split the vertices into two sets. Let's say big S and big T. So this one is S. This one is T. S, the source vertex has to be here, and then there are some other vertices there. The target has to be on the right, and then there are some other vertices there. Okay, there are some arcs that go strangely like that, but then the interesting ones are the ones that go across, and then there are some down here. So they're not really interesting. Okay. Is that roughly your idea of a cut? Most people would probably mark it like. Now, what we have is we have some XAs. So for every arc, there's an XA. So if I put 1 for all the arcs that go from S to T, you can't read it. You won't be able to read it even if I make it larger. Okay, so what I wrote is, I can't read it myself. On these arcs that go in the cut from S to T, I want their decision values to be 1. Okay. And all the other arcs that are within, or that go back, or that are within here, I want their XAs to be 0. Okay. Now, okay, let's just do it. If we do this, if we put a 1 on all the arcs that go from S to T, and 0 on all the remaining arcs in the whole graph. And I'll go back and look at the objective was to minimize. Okay, so the ones that are 1, they contribute their capacity. And the ones where I set this to 0, they don't contribute anything. But what I get by adding all this is the sum of all the capacities of the arcs that go from S to T, and that's exactly how we define the capacity of a cut. Okay, so if I do this, these XAs, if I set them to 1 on exactly the arcs that go across from S to T, and 0 everywhere else, the objective here is going to give me the capacity of that particular cut. So that's a good start. The word minimize is also a good start because we want to find the minimum cut. So we want to minimize the capacity. That's decent. Now, still haven't told you what to do with the y's for the nodes, and I have to remind myself. Okay, so if you're in S, big S is going to be 1. And if you're in big T, your y is going to be 0. Oh, what have I done? I've messed it up. Not hugely, just a little bit. But it'll be a nightmare to fix. Well, it's easy to fix. It's a nightmare to apologize and explain why I've messed it up. Because what I've messed up is the right-hand side here. Because, okay, shame on me. Okay, what I did was, I said that all these right-hand sides are going to be 1 because we're adding the FAs for all the arcs. But we're not adding the FAs for all the arcs. When you look at the formulation here, we're adding the FAs only for the arcs that are leaving S. Okay? So the coefficient is 1 if that particular arc is leaving S. And the coefficient here is 0 if it's not going out of S. Which means that it's going out of S, like here, it's 1. If it's going out of S, like here, it's 1. But the other ones, they have to be put to 0. I apologize for this. Okay, now it's correct. So now with these y's and x's, as I've told you, so yu is 1 in S, and xa is 1 if it goes across. Yb is 0 if it's on the right. You can check that all these constraints will be satisfied. Okay. It's actually not very hard to do, but I don't want to keep you much longer, so I won't do it in much detail. But for example, if you have an arc, just one example, if you have an arc UV, okay, look at this, like this one, that goes from S to T, then its decision variable is 1. Here it's 1, and here it's 0. So what you get is 1 minus 1 plus 0 is greater than or equal to 0. So it's satisfied. And you can check all the cases when you think about it, but, which is probably too late to do in the day to do it now. But if you think about it, you can check that these constraints are satisfied by the solution. So you can check all the constraints to see that any cut gives a feasible solution in this way. And then there's something that's a little bit harder to do, but it's not really hard either, is that you can also check, can also be proved that a basic feasible solution will look like this. Means that will correspond to a cut. So when you get a basic feasible solution, you get zeros and ones on your variable. Well, possibly not, but so the optimal solution will also look like this, and that's going to give you the minimum cut. So conclusion, the dual to the max flow linear program is the min program, and that's great. And you might not appreciate it now, but it's beautiful maths, and that's it. Any questions or objections? Well, if not, then that's the end of linear programming. And from next week, for 4 weeks, I'm taking the 1 o'clock lectures. Philip is taking these ones, which is great for me because I don't have to do so much, only half of the work. Right, hope to see as many of you, well, hope to see everyone from your year in the labs, and have a good week and so on. And enjoy. Whatever you do, enjoy.